My dog is wandering around. Worry about her. Okay, so this week we are going to be talking about energy. This week is going to be focusing on potential energy and kinetic energy and the relationship between the two, and really starting to follow the theory or the law of conservation of energy. So we're going to look into that a little bit. We're going to do a little bit of a warm-up, then we're going to do an intro to Unit 3. We're going to talk about the five main forms of energy. Then we're going to get into those energy conversions, talking about that kinetic versus potential energy. And then we're going to get into that law of conservation of energy. So that's kind of what we have to look forward to. So let's take a look at this picture. And I want you in the chat, please, to describe all of the types of energy that are represented. So why don't you go ahead in the chat, what different types of energy do you see? And while you guys are typing in the chat, I am going to go get my coffee real quick. So Julie, make sure that you are putting it into the chat. You put it into the questions, which is totally fine. You are correct. Mechanical energy is one of them. In the chat, can you explain to me what you see is mechanical energy? Where do you see it and what is it? Okay, and then I'll be right back. Okay, sorry, hold on. Okay, mechanical energy in the windmills, good. And nuclear energy in the sun. Great job, Julie. Exactly. Those are two awesome and perfect examples. So yes, we have a couple of things. Nuclear energy is happening in the sun. Good. And then we've got mechanical energy with the windmills, right? Because that wind is going to get it to be moving, which is mechanical. Good. And then we can make some assumptions here. So if we've got that mechanical energy in the windmills, right, what does that mechanical energy then get changed to? You remember? Potential. Good, good. Yes, so those potential, it's when it's not moving, it has potential energy. Good, good. Yeah, so you guys are bringing up two things, right? So we're talking about kinetic energy, which is movement whenever something is moving. Good. Potential energy is when something is not moving yet, but it can or it will be, and it has the ability to reach this amount of energy. Good, which is potential energy. And then we're talking about the types. So it's a little confusing. We've got potential energy and kinetic energy. Those are the states that an object can be in, right? So those are the states that it's in. It's either moving or it's not moving. Those are two different states. Those are two different like states of energy it's in. But then we've got types of energy, which is kind of what you guys were getting at to begin with. Mechanical energy, nuclear energy. And if we don't know this, that's totally fine. But when those blades move from potential energy to kinetic energy, right? That is mechanical energy. So that's a type of energy. That movement is mechanical energy. How do we then change, or what does it then go to? If we've got mechanical energy, then what do we change that to be able for us to use that energy? Do you guys know? No big deal either way. Electrical energy, good. Good, or chemical energy, right? So good. So we've got these different power towers, and we're going to talk about that, the power grid and everything, and how we get electricity and how energy changes into electricity. But first, we want to talk about the nature of energy. So first of all, energy is all around you. Okay, so whenever there is a movement in the trees, like you see here, if there's actual light versus the waves in the water, this is all energy, and it's always around us all the time. You can hear it as sound. So sound is energy. You can see energy as light, and you can feel it as wind. So these are all examples to start and how we might hear, feel, or see energy. And energy can be in so many different forms. And so we've got a couple to begin with. So when you're using energy, you may use energy when you hit a softball. So if you're playing baseball or softball and you swing your bat and you hit that softball or baseball, that is energy. When you lift up your book bag, you're using energy. When you compress a string, so when you push something together and you push against it, that's compressing, right? Compression. A spring, that's energy. So we've got different pictures here. Remember that every living organism needs energy for growth and movement. How, do you remember from biology, what do we as humans use to have energy in our bodies, and animals and organisms for that matter? Do you remember? It's there's 3 letters that represent it. It's called ATP. Adenosine triphosphate. We start off with using glucose or sugar from eating something else. Unless you're a plant, you can make out your own. And then you take that glucose, you break it down through something called cellular respiration, which is a series of chemical reactions. And then it produces ATP, which is a type of chemical reaction, and it releases energy for our body to move. So even in our own bodies, we are processing a type of chemical energy. Yes, exactly, Julie, exactly. Yep, you got it. So energy is involved. So not only, right, we've talked about what energy is all around us. We talked about when we can use energy, specific examples of using energy. And then we have the nature of energy. So energy is involved when a bird flies, right? Again, that has different types of energies. We're going to get into that. A bomb explodes, is an energy is involved with that. Rain falls from the sky. There's also energy with that. Electricity flows in a wire. So you can see that these are there's energy everywhere. The point we're trying to get through here is we have so many different types of energy. We use it, and it's involved in so many different activities. So what is energy? That it can be involved in so many different activities. What would that energy be? And we talked about this in our previous lessons. So energy can be defined as the ability to do work. Thinking about work is that equation that we learned about, not just like working on homework or working for a job, right? So thinking about work in the terms of physics. So anytime that an object has the ability to do work, it has energy. And then if an object or organism does work, so exerts a force over a distance to move an object, the object or organism uses energy. So really making sure that we understand that anytime there's work, there is a level of energy that's being used. Because of the direct connection between energy and work, energy is measured in the same unit as work. So we know that when you are doing work, so that mass times velocity, or force times distance, I was getting confused with a different equation. Force times distance is also going to be the same unit of measurement. That kilograms, what is mass times velocity? Anyway, we've got joules. That's going to be the unit that we're using. We're going to use joules for both work and for energy. Okay. In addition to using energy to do work, okay, technically this is the power. That's why I was getting messed up. Okay. In addition to using energy to do work, objects gain energy because work is being done on them. So not only do we have to use energy to do work, but then it is also getting energy. And we've got different types of energy. So we've got a couple different forms, and we've got 5 main forms of energy, and they are heat. Okay, so whenever you're feeling heat, whenever you are absorbing the sunlight from infrared light from the sun, if you're touching something that's hot, if you feel it in the air, those are all forms of energy. And we often lose a lot of energy as a byproduct to heat. So thinking about friction, right? Chemical. There is a chemical energy, which is the result of chemical reactions. I already mentioned a couple of times when we turn something, we turn it from one type of energy into chemical energy that we can then harness. Nuclear fission or nuclear power plants, or excuse me, that's going to be something different. A chemical is going to be whenever there's a chemical reaction. When we break down our foods in our body, we get energy from chemical reactions. Electromagnetic. So this is how we get energy when we're talking about electricity and magnets. The moving of electrons in an orbit is going to be a form of energy that we usually use as electricity. Nuclear is what I was getting confused with chemical. So nuclear is the energy of movement in elements between atoms. And so that's why we have nuclear power plants. And the last one, which is mechanical. And mechanical energy is whenever there's physical movement. So that's what we're talking about with windmills. You can kind of feel it when you're just moving your arms in the same direction or the same way over a period of time. You can start to feel tired. You're using energy. Your body is using energy to move things, and things that are moving are creating a sort of energy. So we talk about each one individually. So we've got this heat energy, and this heat energy is is a measurement of how much particles are moving. Okay, so we know that there are particles everywhere, and as they heat up, as the temperature changes, those particles start to move slower or faster, depending on whether you are cooling down or speeding up. So if there's heat, that means that there's more movement within the particles, and that can produce heat. And heat energy can be produced by friction. So when you're cold, okay, so if you're really cold and you can even feel it right now. If you rub your hands together, that friction between your hands is actually generating heat. When you shiver, when you are shaking, when you're so cold, what your body is actually doing is it's contracting the muscles in your body so that it's squeezing and letting go, creating friction between your muscles, generating heat in your body. So heat is definitely produced if you ever touch, if you see a bunch of wheels, like somebody spins off really quickly and you smell that burning of rubber, that's because the friction between the wheels and the ground there was so much heat there that it actually started to, the rubber started to rub off, and you can actually smell it or see that smoke. And that's also heat energy produced by friction. Like I said, heat energy causes changes in temperature and phase of any form of matter. So when water heats up and changes phases, then we can say that there was heat energy. It can cause changes in temperature. Okay. Any examples? That's right, exactly, Julie. That's how people set up campfires without a lighter. Yep, they use flint and rock. Good. So any questions or further examples that you would like to share about heat energy? Because Julie's on it. Anybody else want to share anything? Okay, let's go into chemical energy. So when bonds break, they require energy. So you put in energy when you are creating bonds, and when you break bonds, they release energy. So you put energy in, bonds breaking require energy. So that way you get energy that way. Bond formation releases energy. So energy is out when you create bonds. So the bonds are going to take in energy. This is confusing. When bonds are created, they take in energy. When bonds are broken, they release energy. And that's the same thing that we're seeing here. Bonds that are broken are releasing energy, and then when they form, they take in energy. So chemical energy is required to bond atoms together. So we'll talk about this when you take chemistry, when you talk about the formation and breaking of bonds. There's a little bit more to it, but for the sake of physics, you just need to know that you need energy in order to bond or break. So when bonds are broken, energy is released, right? So when bonds break, the energy is released. Yep. So whenever, that's why when ATP is that constant breaking and reforming of adenosine triphosphate to adenosine diphosphate, and that repetitious cycle of breaking the ATP bond is what gives us our energy to be able to do things. So when bonds are breaking, they release energy. It's like they break it and then like the spark comes out, and when they bond, they need to take in energy. Okay, so fuel and food are forms of stored chemical energy. So we often think of the fuels as like with the hazardous face on them, or food for us. That's how we get energy. That's how we transfer our food into chemical energy that our body can then use. Questions on chemical energy? Electromagnetic energy. So this is power lines, right? This is what we're talking about, electricity. So we've got these power lines that carry electromagnetic energy into your home in the form of electricity, which is how you're able to turn on things if you have electric stove, that's how you cook, that's how we're able to use Wi-Fi, use the computers that are in front of you, is because you will have seen the power grids. They are across the country. And these are all for the specific act of carrying electricity from place to place. And there are different generators. A generator is an area where it is generating power, where we are creating power by moving electrons. So that's really a big thing here, is electromagnetic energy is really about electrons moving. And that's also within the same scope of light. So light is a form of electromagnetic energy. We think of light as the visible light spectrum. That's the colors that we can see. There's a whole range of lights that fit onto a wavelength, and we're going to get into that when we get later into waves. But each color has a specific wavelength, right? The length of their wave is specific. And so we're using that idea with electromagnetic energy and the light and the wavelength, which is a specific type of, that relates to a speed, and that speed is how fast it's traveling. And therefore, it's also a form of that like electromagnetic energy. Each color of light represents a different amount of electromagnetic energy, which we talked about with the wavelength. Exactly. There are definitely different types of lights that we can't see. Infrared, ultraviolet, gamma, right? There are a lot. It's really fascinating. On Netflix, there was a new series that was just put out. I started watching it. It's called Life in Color. It is narrated by Sir David Attenborough, who's one of the more famous, like chances are if you've seen like a documentary, a nature documentary, it's been narrated by, you've heard David Attenborough before, but he's brilliant. And he actually brings in and talks about the different lights and the different ways that animals in the animal kingdom see. And they don't see things the way that we do. And it's actually amazing to hear that, because it's a brand new, not brand new, it's been known for a while, but our technology has been able to catch up so that we can actually create and replicate what images or what it looks like to animals, different animals with different types of views. So some animals can see ultraviolet instead of what we see, right? And it's really, really cool. So electromagnetic energy is also carried by X-rays, radio waves, and laser light. So all different types of light, different waves we consider electromagnetic. So this is what I was talking to you about, the visible light spectrum. Here are all of the different wavelengths. So remember that things can travel via waves. Each wavelength is also corresponds to a speed. And there are all these different types of waves. We've had radar, right? FM radio waves, TV, shortwave, AM radio, infrared rays, like Julie was saying, ultraviolet rays, like like what Julie was also saying, X-rays, gamma rays, and then right in this little section between ultraviolet rays and infrared rays are this little section called the visible light, and that's what we see. And light is actually really, really cool. Just a fun fact, and we're going to get into it later on in a different unit down the road, but we are going to talk about how when we see color, it's actually that object is absorbing every single color except for that wavelength. And then that wavelength gets sent back to your eyes. And that's what we see as color, which is amazing. But I can't get into that too much right now because then that's a whole other thing and we're not there. So we use we can see these different lights, but all of these other wavelengths exist, and that is in energy, in electromagnetic, under the electromagnetic topic or category. Questions on electromagnetic energy before I move on? Okay. If we move on to nuclear energy. So this is what I was talking to you about. They use the actual energy between the nucleus. So the nucleus of an atom is the source of nuclear energy. So remember, the nucleus is that center. The nucleus is made up of neutrons and protons. And so we use that nucleus to create that nuclear energy. So when the nucleus splits, so when you split the nucleus apart, we call that fission. When the nucleus splits, when the neutrons and the protons split from one another, the nuclear energy is released in the form of heat energy and light energy. So once you can split it, then you can release it. And then you can harness that energy. So the nuclear energy is also released when nuclei collide at high speeds and join. So that's called fusion, right? Which makes sense. We've heard of the word fusion coming together much more than we have in fission, which is apart. So nuclear fission and fusion is what generates those electricity, that energy. So when nucleus is splitting apart, when it comes back together, they're releasing forms of energy, and we can take that energy and transfer it into electric energy like we have been. So just like Julie mentioned before, there is nuclear energy in the sun. So the sun's energy is produced from a nuclear fusion reaction where hydrogen nuclei join together to create helium nuclei. So that's really what the sun is. The sun is just this big ball of gas that is continuously colliding and creating, going from nitrogen to helium and creating this the nucleus is joining and parting together. And so we have nuclear energy in the sun. We also talk about it. Nuclear energy is the most concentrated form of energy. I don't know if there are any nuclear power plants in Oregon. I know there are several, and there has been several like around the world. Specifically, if you've ever seen the little mini docuseries of, well, it's not a docuseries, it's a series called Chernobyl. Chernobyl is probably one of the most famous nuclear power plants that you may have heard of. It's in Russia, and they had a nuclear power plant meltdown where there was a lot of series that went wrong, and so that's one that you may have heard of. There's in the news recently, I think that the last one, the last nuclear power plant in New York that was feeding electricity in New York City is actually going to be shut down. There was a couple that have already been shut down, but I believe that this is going to be the last one. So we use nuclear energy in the United States. It's used around the world. It is a very concentrated form of energy, but there's a lot of things. There's a lot of of course, there's some byproduct of emissions, and there's some hazardous, a lot of hazard actually that comes with it. So just keeping that in mind as well. All right, mechanical energy. When work is done to an object, it acquires energy. So remember, when work is done, meaning when you're moving an object in the same direction of movement, that is when work is being done. And so whenever you're doing work on an object, it is also needing energy. It takes energy. So the energy it acquires is known as mechanical energy. Remember that movement, that physical movement is known as mechanical energy. So we think about this when you're kicking a football. You give mechanical energy to the football to make it move. You kick a soccer ball, if you throw a basketball, anytime that you're adding energy to something that makes that object move, that is mechanical energy. So when you throw a bowling ball, you're giving that ball energy. When it hits the pins, that is that momentum. Remember, we talked about the conservation of momentum. Some of the energy is transferred to the pins, right? Transfer of momentum, right? So these are all examples of different types of energies. So we have 5 different types of energies that we just went over. Do you have any questions on any 5 of them? Mechanical, you're going to want to know these too. So if you haven't been taking notes, it's okay. You can pay attention, but you might want to come back to this video recording and just write down some of these things. So making sure that we know the 5. Can you guys give me one of the 5? Go ahead and give it to me in the chat. What's one of the types of energy? So mechanical energy is on the screen. So at the very least, we can be writing down mechanical energy. What's another type? Good job, Julie. Yes, Julie, what's another type of energy that we just went over? Good. Yeah, thermal energy or heat energy. Awesome. What about Sam or TJ? What's another one? What's another one? We have 3 left. Julie's already named 2. Heat, mechanical, what else?
Nuclear.
Great. Nuclear energy is one of them. Awesome. So that's 3. So we're missing 2 more. We've got nuclear, mechanical, thermal, or heat. We also have, what are the last 2? It's how we get
Electric.
yeah, electromagnetic. And we got our electromagnetic energy and chemical. Good. Exactly. So remember those 5. Those are going to be important for you guys to know. So at least have a good understanding of each one before moving on. Okay. So now we have the different types of energy conversion. So what we talk about this is they can be changed from one form to the other. Remember the law of conservation of energy, which I think we're going to get to, but I'll kind of give you a little spoiler first. The law of conservation of energy really has to do with the fact that energy cannot be created, nor can it be destroyed. It's just transferred. We just have different types of energy. It goes from one form to another, which is why we talk about when we use solar energy, we're using thermal energy, we're using that infrared, and we turn it into chemical energy. Same thing with mechanical energy from the wind turbines, right? So changes in the form of energy are called energy conversions. And we already said this, all forms of energy can be converted into other forms. So like I was saying, the sun's energy through solar cells can be converted directly into electricity. And green plants convert the sun's energy, which is electromagnetic, into starches and sugars, which is chemical energy. So again, we are just using things and changing it. So we're just transferring it. So we say that starches and sugars are chemical energy because when we eat those to get that energy, we have to use chemical energy to get our own body energy. So there's other types of energy conversion. So like an electric motor, that electromagnetic energy is then converted to mechanical energy. So we've got a motor in our car that's constantly going to be creating that energy. And then it puts those wheels in motion So then now you're moving, and now you're actually getting that mechanical energy. So we used electromagnetic energy into mechanical. Same thing in a battery. Chemical energy, because the battery is actually just a bunch of chemical reactions happening in that battery. And it's converted into electromagnetic energy. Exactly. So then that's how you're able to power up your devices. And so using chemical energy in your batteries, that's why they say battery acid, and making sure that you keep your batteries in a good room temperature is important. Because otherwise they can, if you got like some of the battery acid leaks, it's really, really dangerous because it's just a bunch of chemicals. And they're just reacting over and over and over again. And that's how you get into the electromagnetic energy. And then the mechanical energy of a waterfall is converted to electrical energy in a generator. So a generator is when you're taking it from one form and putting it into another. That mechanical energy, the actual act of a waterfall falling, can then change something going on in the generator, and it produces electrical energy. It's why a lot of what we use here are dams. And that's not the same thing as a waterfall, but it's the movement of water. The movement of water is creating movement in some sort of turbine, some sort of thing that's going to go around, and then that's going to be converted into that electrical energy. So we talked about a car. So here's an example. We need to have fuel, right? So every single time we need to give it something to react with in order to give it off. So we need to put gasoline in our car, and we have oxygen, and then it combines through something called combustion. So then what we have is kinetic energy of movement. So our wheels start to go, we start to move from one place to another. And then we have heat energy. So if you've ever opened your car and the engine is really, like the hood of it, and the engine is really, really hot, because some of that energy got lost to heat. But then the waste products are water. So we usually see like some sort of condensation, and carbon dioxide, which are those carbon emissions that we talk about, and how that leaves the car. So it started as this. It went through some of the combustion. It went through some of the changes. It formed into different types of energy. So heat energy, kinetic, well, the heat energy, and then these byproducts. And then it changed it from stationary, which is potential, into kinetic energy of movements, right? So two phases. In an automobile engine, fuel is burned to convert chemical energy into heat energy. The heat energy is then changed into mechanical energy. Okay. So we've got chemical to heat to mechanical is one of our examples of energy conversion. So it went through 3 different types of energy to get to what we wanted it to do. Like I said, there's 2 different states that energy, or phases that energy can be in. So that is the most common energy conversion is the conversion between potential and kinetic energy. So all forms of energy can be in either of these 2 states or phases, right? You've got your potential energy, which is the one that has the ability to do something, but it's not yet, right? And kinetic energy, which is when it's actually moving. And the great thing is these 2 are complementary to each other. So if they start off half and half, if the kinetic energy speeds up, that potential energy goes down, and vice versa. Okay, so they're always transferring back and forth between these 2 states. So kinetic energy is the energy of motion. Potential energy is stored energy, right? You've got this, you can do it, but you're just not using it yet. We talk about a kinetic energy. We know that that's when something is moving, it's in motion. The faster an object moves, the more kinetic energy we're going to get. The greater the mass of a moving object, the more kinetic energy it has. So kind of playing with that relationship, right, of work, and understanding that the more energy it has, that means it either needs to be moving faster, it needs to have a higher mass, or a combination of both. Kinetic energy depends on both mass and velocity, which is just what I said. And we have an equation. So let's go ahead, and I'd really like for you guys to write this down. So please write this equation down, because we've got this equation that we're going to be using. So kinetic energy is equal to 1/2 of the mass times velocity squared. So if we break this down into the units, so if we break this down into the variable, so 1/2 m, which we measure in kilograms, times velocity squared, which is meters squared over seconds squared, that's going to give us our equation of 1/2 mass times velocity squared. And it's really important that you always remember that this velocity is squared. Okay. And then that means that we get these units, kilograms times meters squared over seconds squared, and that is equal to joules. Okay. Looking at our equation, what's going to have a greater effect on kinetic energy? Is it going to be mass or is it going to be velocity? And then tell me why. Which one is it going to be? And you can type this in the chat if you would like. So let's take a look at this. Do you think that the mass that's being cut in half is going to have a greater effect on kinetic energy? Or do you think the velocity that's being squared is going to have a greater effect on kinetic energy? If you wanted to make something go faster, if you wanted something to have, I should not say it that way, if you want something to have more kinetic energy, what are you going to change? Are you going to change how fast it is? Or are you going to change how big it is? Are you going to want to change something that you're going to have to cut in half? Or are you going to want to change something that will be doubled and times itself by 2? You're going to want to change the velocity, right? The velocity is going to have a bigger effect because it's the one that is being squared. And if you're squaring something, that's going to have a bigger effect than if you were to increase the mass, which is just going to be halved anyways. So the velocity is going to have a greater effect. So here is potential energy. So potential energy is stored energy, stored chemically in fuel, in the nucleus of atoms, and in foods. So these are all opportunities where they can, but they're not yet, right? Or they're stored because the work done on it, stretching a rubber band, meaning that's stored. As soon as you let go, it's going to release. Winding a watch, which I don't even know if you guys know what that is anymore. You used to have to wind your wristwatch to give it that energy again. Now we just have like fancy Apple watches and e-watches, so you just charge them. But there was a time where you actually had to wind your watch to give it that energy that it needed to keep going. Pulling back on a bow's arrow. So if you're in archery, if you pull back and you just hold it there, that is that stored energy. You're creating that tension between the string that once you let it go, it's going to then transfer into a different type of energy. But that one part where it's holding it is what's going to be the stored. Lifting a brick high in the air. So if you are bringing something above the ground, you are going to be creating or increasing that potential energy. So we have something called gravitational potential energy, and that is when the potential energy is dependent on the height. So the higher off the ground it is, the more potential energy it's going to have because that force of gravity is going to be acting on it. We also have that energy stored due to being stretched or compressed. It's called elastic potential energy. I was just using that example of pulling that bow back. it's elastic, right? Compressing is a spring. So like this rubber band, if you're stretching it out, you're creating elastic potential elastic potential energy by stretching it. And when you wind a jack in the box, if you wind it, you're compressing a spring, and that's going to let go and change into energy. But as you're winding it, it's creating elastic potential energy. So we have two different kinds. We've got gravitational potential energy and elastic potential energy. So when we talk about gravitational potential energy, this equation is GPE to represent gravitational, and that is mass times gravity due to times the acceleration due to gravity, and height. So height, the higher off the ground you are, and depending on where you are, so long as you're on Earth, that G is always going to represent 9.8, and then the mass of the object. Again, we use the word or the term joules to go ahead and use it as that unit. A waterfall, a suspension bridge, a falling snowflake, anything that is really falling is going to have gravitational potential energy. Diving off of so if you stand on a 3-meter diving board, so meaning it's 3 meters off the ground, you have 3 times the gravitational potential energy than you had on a 1-meter diving board because you were 3 times the height, right? So kind of understanding that relationship between the height of an object and how that the higher you are, the more gravitational potential energy you have. So we're going to do a practice problem. We're going to just do a couple because I see that we're already kind of a couple minutes away. Let me just see how many we had. Great. So we're going to work through a couple of these. And so we're going to go ahead and practice. So when we're taking a look, calculate the kinetic and the potential equation. And this example is coming right from your book. So if you guys haven't already, this is the book that we got with our Fuel Ed kits. You should still have it. Should have come with your lab kit or separately when you got all your books. And this is where you get a lot of practice problems. And so this one is out of page 138. So if you have it handy, I really recommend that you go for it because it's going to have it right there. So we have a 2.25 kilogram apple falls out of a tree 6.1 meters high. The apple is traveling 11 meters per second just before it strikes the ground. What is its potential energy before it falls? And what is its kinetic energy just before it reaches the ground? So the first thing we're going to answer is what is its potential energy before it falls? So we need to fill out our givens, our unknowns, the equations, and finally our solution. So in our given, right, what information do we already know from this why can't I think of this problem? What do we already know? What variables? What variables? So like, do we have mass? Do we have velocity? Do we have height? Do we have energy, right? What do we have? What does this problem give us already? Let's go ahead and switch over to a whiteboard where I can kind of show you how to do this math. So I know that you can't see it, but I have the screen open on my end. So I'm going to write down what the givens are. So according to our problem, we were told that the mass, right, that a 0.25 kilogram apple, which automatically the kilogram unit should have given it away that the mass of the object is 0.25. So the kilograms is the unit for mass. So we're going to write that down for our M. So we know our M. If you continue reading the sentence, it says that a 0.25 kilogram apple falls out of a tree 6.1 meters high. So high represents height. So we can write down our h is equal to 6.1 meters. So there we have our another given. What else do we know? It says the apple is traveling 11 meters per second just before it strikes the ground. So we're going to put down the velocity is 11 meters per second. So these are the givens. Now let's look at what we want to know. So we are now trying to solve for the unknown. What is it that we're trying to solve? What does our problem tell us that we're going to find? It wants to know the potential energy. So what kind of potential energy is it going to be? Is it going to be the gravitational potential energy, or is it going to be elastic energy? What are we doing in this scenario that's going to tell you one or the other? And then the other one is kinetic energy. Do you guys know? Is this going to be gravitational potential energy or elastic potential energy? Millie, enough, Millie. So it's going to be gravitational potential energy because it has to do with gravity. It has to do with falling, right? It's not stretching. It's not being compressed. So it just has to do merely with the fact that it's the height off the ground. And that's going to give us our, to know that we're going to be looking for gravitational potential energy. I'm also writing down that G is equal to 9.8. That is a given that we should know because it's saying that it doesn't say anything about being anywhere else but Earth. And in that case, we're always going to use this 9.8. So now we need to know the equations. So can you guys tell me what equation it is for gravitational potential energy? I would really appreciate some participation. So what is the equation for gravitational potential energy? And I'll wait until someone gives me the answer.
I don't know the answer, so I'm paying attention, but I don't know.
Did you have a chance to write it down, Sam, the equations that I went over?
I went to the bathroom a little bit ago. I don't think I wrote that down.
Okay, well then why don't we go back to it, because it's something that we really need to make sure we have written down so we are ready to go for when we have it. So here is the equation for kinetic energy. So 1/2 mass times velocity squared. So you're going to want to write these down somewhere or take a screenshot or a picture with your phone, but you're going to want to know these equations. So I'll give you a second. So let me know once you have it written down, okay?
Okay, I have that one.
Great. And potential energy, and that equation is this one. Mass times G, which is that 9.8 times height.
Okay, I have that.
Great. Okay, so then if we go back to our problem, it's saying what is its potential energy. So if we look at our whiteboard that we started, what is one of the equations that we're going to be using? Let's do
GPE, that one?
Yep.
Equals MGH equals M kilograms times 9.8 mass times S squared times H parentheses M equals kilograms mass squared slash S squared equals J.
Great. I love that you went and read all of, like, you broke it down because it is MGH, and then you included the units and explained how those units all relate to each other too. So that was awesome. So mass times G, which is 9.8 times height. So what is the gravitational potential energy for this? Well, in order to do that, we need to take our knowns and put it into our equation. So we're going to put 0.25 . times G, which is 9.8, times the height, which they said was 6.1. So would one of you guys like to do that multiplication really quickly and then let me know what you get? And then just round it to the second decimal place.
Wait, is that 0.25 times 9.8 times 6.1?
Yes.
Okay.
Let me know when you get it.
You want me to round up to the nearest what?
Second decimal.
Okay. 14.95.
Perfect. And then what's the unit?
I
You
don't
told me what the unit was before.
kilograms.
Close. Joules. So remember the joules is the kilograms times that unit, right? So when you break it down, it's going to be in joules. Good. So that was for GPE. So what about, it also is asking us what is the kinetic energy right before it hits the ground. So for kinetic energy, do you have that equation, Sam?
Yeah. KE equals 1/2 mass times velocity squared equals 1/2 m kilograms times velocity squared. M squared slash S squared equals kg. M squared slash S squared equals joules.
Yep, you got it. So the equation is 1/2 mass times velocity squared. So if we take a look at our data, right, we can put in our mass and we can put in our velocity. But it's important that we pay attention to the rest of this equation. So unlike the potential energy where we just multiplied across, this one, we actually have to do a couple of order of functions before. So we've got 1/2 times 0.25 times velocity, which is 11 squared. So we're going to want to do this first. So we're going to want to do 11 squared first, okay? Order of operations. So we've got our squares first, right? And then what is 11 squared?
121.
Good. It is 121. So we can put that right above it. So it is 121 times. And then what is half of 0.25?
0.135. I mean 0.125.
Yep, you got it. So it's 0.125. So now we want to multiply these numbers together. So we're going to do 0.125 times 121, and that's going to give you your kinetic energy, which is, let me know if you have it.
15.125.
Perfect. We round to the second decimal, so 15.13 joules. And those are your two answers. Great. Pretty straightforward, I know. I am going to challenge you. I'm just looking at the time. And I'm going to challenge you to go on to page 138 in your book I want you to try some of those problems. So we're going to be getting to conservation of energy in small group. In small group, we're going to go over that lab that we started to go over yesterday. And then we're also going in that small group, we're going to be practicing all the different equations. And I'm going to be posting this. I just want to show this to you really quickly, that kinetic versus potential energy. There's only potential energy in this point. And nothing is in kinetic energy because it's not moving. But then once it starts to move, then you're going to see these bars go back and forth, and they're going to complement each other. So between KE and PE, so kinetic energy and potential energy, it's always going to equal 100, or the total amount. But how much of it is PE and how much of it is KE is going to change depending on where this guy is along the track. So there are more examples going up and down. The law of conservation of energy, I already said, energy can be neither created nor destroyed. It can only be changed from one form or another. It doesn't just disappear. It means that scientists need to look for it, which then leads to a lot of other discoveries. More information, Albert Einstein said that mass and energy can be converted into each other. He showed that if matter is destroyed, energy is created. And if energy is destroyed, mass is created. And that's where he gets this idea of E equals mc squared, which is a pretty famous equation. You may have seen that before. And that's everything that I have for you today. I know it's a little longer of a lesson, but it is 11 o'clock, and I encourage you to do some of those practice problems and go through your lessons. And then otherwise, that's all I have for you today. I hope you have a wonderful Tuesday, and let me know if you have any questions. And for small group, we're going to continue with doing our lab and getting that lab done. All right, so if you have no more questions, then you are free to go.
Thank you.
You're welcome, Sam. Have a good one. Bye, TJ.